Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to do radioactive decay kinetics. So this is going to deal with how to calculate how quickly or the rates of decay of certain substances when you're given certain information like a starting amount and ending amount, and you're given the half-life and things like that. So let's get started. So in problem number one, we're given a sample of plutonium 236, and we are told that a sample contains 1.35 milligrams of this stuff. And we're also told it's an alpha emitter, has a half-life of 2.86 years. Then it's asking what mass of the Pu-236 is left after 5 years. Okay, so we've got the half-life. We want to know how much is left after 5 years. We're given the initial amount. So what do? Well, the two equations that are going to be very important is this one, the half-life equation, and this one here. These are actually derived from your rate laws that you learned from your kinetics. So if you learned kinetics, or in a previous video, if you watched my videos on kinetics, and you learned about the integrated rate laws for first order, second order, and zero order reactions. And so here we're using the first order rate reactions, and we're using them to apply them to decaying. So here we have the half-life equation. So we have the half-life is equal to 0.692 over K, the rate constant. And so we can use this to find K, because once we find K, then we can plug this in with the information, and they want to know what mass of this substance, Pu-236, is left after 5 years. Well, they gave us the time in years. We'll figure out K right here using the half-life, which is given 2.86 years. And so once we find K, we can plug that in. We'll plug in the 5 years. And then what we need to find is the amount left. And so here we have the number of nuclides after a certain time over the number of nuclides initially started with. So because we're dealing with here the same atom, then we can replace the number of nuclides or moles of nuclides with mass, because since we're dealing with the same nuclide on both top and bottom, if you use your molar mass to convert both of these to grams, molar mass is going to cancel out anyway, so it's going to be the same ratio. So you can substitute numbers of nuclides with mass that you're given. So here we're given milligrams. Okay, so let's get started. So here we're going to start by plugging in the half-life they gave us. So 2.86 years, okay? That's going to be equal to 0.693 over K. And now all we need to do is solve for K. So we're going to solve for K, multiply both sides by K, divide both sides by 2.86 years, 2.86 years, and we get K is equal to, let us calculate that. And so K is going to be equal to 0.2423. 0.2423, underline the 2. We're keeping an extra digit to avoid rounding errors. Okay, so now that we have K, let me double check the units. This is per year, since we have years on the bottom. This is per year. Okay, so now we have K. So now we can plug what we know into this equation here. So this is again the integrated rate law for first order reaction. So here it would be the ln of n, the amount after a certain time. So that's what we need to find, the amount left after 5 years. So we're going to solve for the amount nt. The initial amount we started with is 1.35, so we'll put that 1.35 milligrams, and that's equal to negative k. K we just found is 0.2423 per years, multiplied by the time, which is 5 years, 5.00 years. So we see that the years are going to cancel out, and now we're left with milligrams. So when we solve this, we're going to end up with milligrams of our units. So this is going to be equal to, if we multiply that out, it's going to be equal to, let's see, that's going to give us 1.2115. So 1.2115, well, that's going to be negative, so negative 1.2115. And so what we're going to do is we're going to solve this by raising everything to the e power, right? So if we say, okay, e, and this is going to be ln of nt over 1.35 milligrams, that's going to be equal to e, and this is going to be negative 1.2115. And the reason I do that is because I need to get rid of the natural log. And it's the same thing with the log base 10. So in that, if I have a base 10, log base 10, then I would raise that to as a power of 10. And then the log base 10 and the 10 being a power of 10 is going to cancel each other out. So it's like taking the square root of a square. They undo each other. So if you square something and then you take the square root of it, you get back what you had before. So it's the same thing here. I had n over t over 1.35 milligrams, taking the natural log of that. If I take this whole thing and raise it as a power of e, then the e and the natural log cancel out, and I get back what I had before. And so if I use this space over here, what I end up with is I'm going to have n sub t over 1.35 milligrams, and that's going to be equal to e to the same power, negative 1.2115. Okay, so now I have e to negative 1.2115, and then I just use my calculator to calculate what that is. And then now I multiply both sides by 1.35 milligrams, and I'll get the amount left over after the 5 years. And when I calculate that out, I get 0.402. So the number of milligrams, I'll write it up here. So n sub t is equal to 0.402 milligrams. Let me double check to make sure I'm writing that down correctly. 0.402, yep. So then this is the amount that's left over after 5 years. So again, to recap, I use the half-life equation here to find k. So I plug in half-life, solve for k, and I get k is equal to 0.2423 per year. I then take k, put it into this equation with the other information. So ln of nt over 1.35 milligrams is equal to negative, and then k multiplied by the time that I'm given. And then I solve for n sub t. Okay, what about the second question? So the second question, coming back to here, like how long will it take for the 1.35 milligrams to decay to 0.100 milligrams? Okay, so now we're starting with the initial amount they're giving me an amount after a certain amount of time, and they want to know what is that amount of time. So we're going to go back to this equation here, and we're going to apply it again. So here, this time, I have n of t. They're giving me n sub t, which is 0.100 milligrams over, and what's the starting amount? The starting amount, again, is 1.35. So 1.35 milligrams. So the natural log of this ratio is equal to negative, and then it's the same K value because I'm dealing with the same substance, same K. So that's going to be negative 0.2423 per year multiplied by the time t. And the time t is what I need to find. So now all I need to do is solve for this, divide by this, and I'll get t. So if I do that, okay, and I get negative 2.60, so this is going to be negative 2.60, what else? 2689, and some other digits, and that's going to be equal to negative 0.2423 per year times the time. I divide both sides to get t, and when I do that, I get 10.7 years. So, 10.7 years. So it'll take 10.7 years for this to decay to 0.100 milligrams. So I hope this was helpful. If you like this video, if you like my videos, my channel, please please like, share, subscribe, hit the notification bell, make a comment in the comment section. Thanks for joining me, and I'll see you next time.